one of the main, well, the main objective, the key objective of our genetic surveillance project is ultimately to provide the public health officers with actionable knowledge. And by actionable, we mean things that they can easily translate into interventions. And as Varanya mentioned earlier on, it's tricky to do that when you got a spreadsheet full of genetic mutations and so on. So actually, we've been putting a lot of effort, a lot of attention to converting genetic data into, you've seen some maps over there, into in generally different types of informative infographics that can help public health officers make better or faster decisions. So Ethan Booth here is a research scientist in our team, and he's actually been working on developing some of these tools. So now he will give you an overview and, in fact, a demo of some of the tools that we've been developing to produce maps and other outputs, both you know, on your laptop, but also on the web. So Ethan, to you.
All right. Okay. Thanks, Olivo, for the introduction. So the topic of my presentation today is interactive tools for surveillance of drug-resistant malaria. And in this talk, I'll be presenting a couple of tools that we've developed. One is the GRC-Malaria R package, which translates the genetic surveillance data in the GRC into genetic epidemiological maps. And the other tool is a web application that's powered by the GRC-Malaria R package. Right, so to give a brief overview, I'll first give a background on anti-malarial resistance surveillance and how the GenRe-Mekong project fits in. And then I'll give a brief overview of the rationale behind development of the tools that we developed. And then I'll go over the functionalities of the couple tools. And then I'll give a video demonstration. And then lastly, I'll mention the limitations and future directions of one of the tools. Right. So I want to start by asking how anti-malarial resistance is detected. And to me, there are three general ways resistance can be detected. So the first method would be clinically, and this can be by noting an increased rate of treatment failures, for example, through a therapeutic efficacy study. The next way would be phenotypically, and this could take the form of a drug susceptibility assay and it takes place within lab conditions. So you would eliminate most, if not all, of the confounding factors in testing for resistance. And lastly, our genetic methods, for example, PCR or amplicon sequencing. But with genetic methods, you're not detecting resistance directly, but markers associated with resistance, or in ideal situations, the markers that give rise to resistance. And of these three methods, the most high throughput and cost-effective method would be genetically. And so that's what most surveillance activities implement. And that's where the GenRe-Mekong project fits in. So like Varanya mentioned, we are a collaborative endeavor between the GenRe-Mekong core team and our partners. And what we do is after the samples have been collected and processed, we compile the genotype data, and then we analyze the data and deliver insights back to the partners so that they can use these insights to inform malaria control activities and policy making. And one of our key outputs is the genetic report card, which is a large spreadsheet that contains genotype data as well as other metadata of every single sample that's been collected and processed in the project. And the genetic report cards contain data pertaining to geographical metadata and other metadata, as well as genotypes for 35 loci associated with antimalarial resistance and 101 loci of the genetic barcode, and as well as the predicted resistance to different antimalarials based off of the drug resistance genotypes. Right, so for the most part, we publish the genetic report cards in Excel, and you could use Excel for analysis, but Excel is not really suited for the type of analysis that would benefit a control program. And Excel also doesn't take advantage of the geographical information available in the data set. So to address this, we developed the grcMalaria R package, which is able to translate the rich genetic data in the GRC into genetic epidemiological maps. And these maps would go on to inform malaria control activities and policy making. But I'd like to ask further, how does genetic epidemiology assist with malaria control activities? And so Olivo developed a framework that kind of listed the different kinds of activities of genetic epidemiology, as well as the different activities of malaria control programs, and then map these activities onto each other to kind of give an idea of how genetic epidemiology can assist with control activities. And so, as you can see, many activities of genetic epidemiology helps with control program decision making. For example, one of the key strengths of the grcMalaria R package is to analyze and visualize the frequency of genetic markers. And as you can see, the analysis of genetic markers assists with various activities of malaria control programs, such as to select a drug policy or to monitor diagnostics efficacy. Right, so the grcMalaria R package contains the ability to create maps of different features of the genetic data. So firstly, the grcMalaria R package could produce a map of the different samples of the sample count. As you can see here, this is a map of the different, the distribution of samples collected in Cambodia, Laos, and Vietnam. It can also produce maps of predicted resistant up to 10 different drugs. So here you can see a map of the same geographical regions, but here of resistance to piperacin. It can produce maps of allele proportions of up to 35 different loci. And here you can see the allele proportions of the plasmepsin 2,3 amplification, and as well as maps of higher level population genetic features, such as genetic diversity or genetic connectedness between sites. I'd like to also note that the grcMalaria R package isn't limited to data from Southeast Asia, but as long as the data is in the appropriate GRC format, the grcMalaria R package can produce genetic epidemiological maps for that region. And we've already went ahead and converted the PF7 dataset, which contains up to 20,000 samples, into the GRC format and produced various epidemiological maps of Africa, as well as South America and Oceania. In the future, we'd like to convert further data sets, producing more maps, more genetic epidemiological maps of more regions, as well as more accurate maps of existing regions. So I'd like to give a quick demo of how a user would go about using the grcMalaria R package. So to start, a user would have to execute these two functions, which initializes the genetic report card. And say a user was interested in looking at chloroquine resistance in Laos, so a user would execute this these two functions, the first of which selects samples that originated from Laos, and the second function generates a map of the predicted resistance to, let's say, chloroquine. And after execution, the package would generate this map right here, which shows the prevalence of chloroquine resistance at the district level in Laos. So as you can see, chloroquine resistance is almost at fixation level or at fixation level at many of the districts. So let's say this user wanted to compare between 2018 and 2019. So the user would just have to specify a variable that specifies the two time periods and then supply that variable into the mapping function. And the package would produce these two maps, which shows chloroquine resistance prevalence in 2018 and 2019. So as you can see, there's not much change in chloroquine resistance. Lastly, if a user wanted to look closer at a specific province, say Attapeu province, and they wanted to look at the microhaplotype of the PFCRT, which gives rise to chloroquine resistance, they could select samples originating from that specific province of interest and then supply the name of the selected sample set into the function. In this case, the function would be map allele proportions, which produces a map of the proportion of alleles. And after execution, the package would produce these two maps, which shows the change in the PFCRT alleles between 2018 and 2019. So as you can see, the R package is quite straightforward to use. It's very simple. And also it doesn't require a lot of computing power as well. But the R package isn't really suited for data exploration and hypothesis testing by partners. And so to complement the abilities of the R package, we developed or are in the process of developing a web application which allows users to quickly explore and test any speculations or hypotheses they might have. So the web application contains key features of the GRcMalaria R package that are relevant to a control program's activities, such as the ability to visualize and map sample counts, the prevalence of resistance, the prevalence of mutation, as well as the proportion of alleles. So I'd like to first show you the graphs produced by the web application. So these are 4 graphs produced by the application. And on the upper left corner, you can see a graph of sample counts of Thailand, Cambodia, Laos, and Vietnam. As you can see, the samples are collected all throughout the years, but with a high sample count in 2017 and 18. Next is the predicted resistance to artemisinin. And here you can see the graph of the percentage of samples that are predicted to be resistant to artemisinin in Cambodia and Thailand. Next, the application is able to produce a graph of the prevalence of mutation. Here, the prevalence of the ferredoxin D193Y mutation is shown for Cambodia, Laos, Vietnam, and Thailand. And lastly, the application can show the proportion of different alleles. Here I've shown the proportion of Kelch alleles. So as you can see clearly, the expansion of the C580Y Kelch 13 allele starting in 2007 and dominating the region by 2019. Moving on to the mapping functionality, the web application is able to produce maps similar to the GRcMalaria R package, but it also contains a unique feature that allows users to compare maps side by side, and this facilitates hypothesis testing or exploration between different time periods or different studies. So, or any parameters that the user wishes. Right, so I'd like to give you a small video demonstration in the next slide.
Hi, in this video demonstration,
I'd like to show you the different features that the web application offers. And so if you click on Start Exploring, it will take you to the first visualization, which is a visualization of the number of samples collected from Cambodia, Vietnam, and Laos over the years. But before I talk about the visualizations, I want to spend a little time talking about the user interface and the selections on the left-hand side. Here, you can see at the top 3 options. The graph, as we can see now, there's a map, which displays a single map, and there's a compare maps, which displays 2 maps side by side. Below that, users can select the samples and the feature of the samples that they want to visualize. In Select Samples, users can select the country, the province or states, the studies, and the time period from which the samples are collected. Here, as you can see, we've chosen Cambodia, Laos, and Vietnam. When users select the countries, all the remaining fields are automatically updated. So for example, if I click on Vietnam, all the provinces, studies, and the years that the samples were collected from in Vietnam will be automatically chosen. And for users to see the changes they've made, they must click on Display Changes. But let's return to the original selection. Right, so after users made their selection, they can click on the other category of selection is the selected feature, which is the feature of the samples that they would like to see visualized. There are 4 different features. There's a sample count, which is the number of samples the user have selected. And there's drug resistance, which is the percentage of samples that are predicted to be resistant to a certain drug. Here we can see that there are 10 drugs to choose from, and that the selection related to the features will automatically appear once you've selected the feature. So for instance, if I select mutation instead of drug, this bottom selection will change the mutation, and the same for allele proportion. Users can actually click on the heading here to see that which alleles are associated with resistance to which drugs. All right, next, users can see what selections they've made here. If they click Show and Hide, users can see what country, what province they've selected, and what study they've selected. And also the year and the features they've selected. Lastly, users can see how many samples are used in the visualization on the right-hand side here. There are 6,340 samples that are used to create the graph on the right-hand side here. So let's now look at, say, artemisinin resistance in these 3 countries. We can see that artemisinin resistance in these 3 countries roughly follow a similar trend. So with as we know, Cambodia was the first country that was detected to have artemisinin resistance. By 2015, the resistance had spread to Laos and Vietnam, and we can see the prevalence of resistance increasing following Cambodia and plateauing at 80 to 90%. The cool thing about Plotly, which is the graphing library you see here, is that you can actually interact with the graph. So if I wanted to, say, isolate Cambodia, I can just double click on Cambodia here, and you would only see Cambodia. Or if I wanted to make Vietnam disappear, I can just single click Vietnam at the legend, and I can remove Vietnam from the graph. Now let's look at piperacin resistance.
Right, so Cambodia is the first place that piperacin resistance was detected in. And as we can see over the years, starting perhaps in around 2014, this resistance had spread to neighboring countries in Vietnam and Laos. So we can see piperacin resistance increasing in these countries as well, despite Laos having used artemether lumefantrine within this period, which is a different drug. So this demonstrates a spillover of resistance. Right, so let's visualize this as a map. So we can click on single maps here. And we can see the geographical distribution of piperacin resistance within the countries we've selected. Now, I would like to make the markers here a little bigger. So to do that, I can click here, which only appears after clicking single maps or compare maps. So if you click that, you can increase the marker size among other things relating to the map graphical mapping parameters. So to see the changes you made here, you must click on display changes. All right. So here you can see there's very high resistance to piperacin along the Cambodian border, on both sides of the border also. And as we move farther from the border, we can see that resistance declines. So in the northern zone of southern Laos, we can see there's a low resistance to piperacin. And here we can also see the same pattern in Vietnam. So I'd also like to note that the selections made in the previous visualization also carries over automatically to single maps. So let's look at CALCH13, which is a gene that carries many alleles that can give rise to artemisinin resistance. So allele CALCH13. All right. Okay. So here we can see a similar pattern where along the Cambodian border, there's a very high prevalence of the C580Y CALCH allele. Right. What if I would like to see it not geographically, but for the proportion of CALCH alleles for different years? So what I can do is I can go back to graph. And here I can see the proportion of the different alleles of 4 different alleles, and the other one aggregated over time, with the 3 countries being aggregated. So here we can clearly see that the wild type CALCH13 allele starts to decline. And here we can see the expansion of the C580Y CALCH allele from 2010 to 2019. Now let's look at this geographically once more, but let's compare between 2 time periods. All right, so here we have 2 identical maps. Let's select the time periods, 2016 to 19, and then for the first map, let's choose 2011 to 2015. The map on the left-hand side is the proportion of CALCH alleles within Vietnam, Cambodia, and Laos for 2011 to 2015, while on the right-hand side, it is for 2016 to 2019. And here we can note a couple of things. We can see that in the earlier period, there's a much higher number of different CALCH alleles than the later period. And this reflects a higher diversity of CALCH alleles in the earlier period. And we can note the concentration of C580Y Kelch allele in Western Cambodia and in Vietnam. And as we can see, the C580 allele has spread along the border of Cambodia and Vietnam, and this has caused the minor other alleles of Kelch to decline in frequency as well. And so here we can see clearly that as one moves away from the border, as I've mentioned, the proportion of C580Y decreases. All right, so let's look at a couple different countries now. Let's look at Indonesia and Papua New Guinea. So let's return the single map and let's select Indonesia and Papua New Guinea. Now, say we were interested in sulfadoxin resistance. Now, as we can see, there's quite high resistance to sulfadoxin all over Papua New Guinea and Indonesia, Papua. Now, say I would like to know what mutation gives rise to the resistance I'm seeing here. What I could do is I could go to compare maps. Then I could select Indonesia and Papua New Guinea for the comparator map. And if I'm not sure what mutation is associated with sulfadoxin resistance, I can click on this link to bring up the table, and sulfadoxin is right here. So there's quite a few mutations related to sulfadoxin resistance, but for the intents and purposes of this demonstration, I will choose DHPS K540E. All right, so here I can see that there is a correspondence, though not a 100% absolute correspondence between sulfadoxin resistance and DHPS K540E mutation. And I think this is because sulfadoxin resistance can be caused by more than one mutation. And so mutations, the resistance to sulfadoxin at, say, Isepik, Madang, and Myeonbay may be caused also by another mutation that gives rise to this resistance. All right, let's look at Africa now. Let's look at the whole of Africa. And let's change the map parameters while we're at it. And let's look at, say, chloroquine resistance. Chloroquine resistance, okay. All right, so here we can see the prevalence of chloroquine resistance all over the sites in Africa. So I would like to note a couple things here. So as you can see in West Africa, there's high resistance region-wide, except for this small pocket of chloroquine sensitive samples or chloroquine sensitive sites. On the other hand, there's East Africa, which displays a gradient of chloroquine resistance from high resistance in the north, and as you move southwards, resistance gradually declines until there is no resistance detected in the south of East Africa. So let's say I also wanted to look at the mutation that gives rise to chloroquine resistance. So I can select all the samples from the African countries, and then I can select the mutation that gives rise to chloroquine resistance. So that would be CRT K76T. So here we can see two maps of Africa, one showing the resistance to chloroquine and the other showing the prevalence of the CRT K76T mutation. And as you can see, there is a very tight correspondence between the prevalence of the mutation to the prevalence of chloroquine resistance. Now let's zoom into West Africa. All right, so here we can see the chloroquine resistance from the samples collected in West Africa. Now here we can see that there's quite high resistance region-wide, with a pocket here of chloroquine sensitivity. Now, say I wanted to explore why this might be the case, I want to investigate, and say I think, well, perhaps samples collected from these locations were collected before chloroquine resistance emerged and spread. So what I could do is I could return to graph, and I can see that the country with the lowest chloroquine resistance is this country, which is Ghana. And now this graph disproves my theory, because the samples collected from Ghana are contemporary to the samples collected from other countries that are shown in the map. And so there must truly be a pocket of chloroquine sensitivity, and not merely that's not merely the result of sampling bias, or at least not merely to sampling bias from different time periods. Right, so I hope this is useful for you, and I hope this is informative about how one might go about using the web application. Thank you very much for watching this video. Bye-bye.
Right, so before I finish this talk, I'd like to give a brief limitation and future directions for the web application. So one big limitation is that it is still a prototype. So we are still in the process of developing it and making it more robust. There's also an issue with well, not an issue, but a limitation with how recent the data is. So the data that is used in the application is not the most recent data. It's using the published data. And for Cambodia, Laos, Vietnam, that only goes up to 2019, I believe. And also, users can't interact with the map that's produced. So in the future, we'd like to make the web application more robust, improve its performance. Then after that, we'd like to release it to the public, and also make partners able to visualize their own data privately. And lastly, we'd like to add some more features, such as the ability to analyze clusters and other analysis as well. So that's all from my talk. Thank you very much. And you're all invited to use the web application, test out the web application right there at that table. Thank you very much.
Thank you very much, Ethan, and thank you very much for the effort you put in to actually make the prototype available for this talk, because it's still work in progress, and you know, we really hope to have much more to show you at the next opportunity. But you are welcome to use the tool after during the breaks and so on. Questions? Yes, Esther, would you like to ask a question?
So I've got two questions, rather cheekily. First of all, can your web app be used for data that are not in the GRC format? And if not, are there plans to be able to do this?
Well, I think what we have done is to basically convert data into the GRC format. It's not a difficult format to use. So I mean, right now there are no standards that can be followed. So I mean, I can't say, yeah, the library will just accept anything, because just not feasible. I think what we will be looking at is to work with groups that are defining the standards, and you're very, very aware of that. And hopefully we'll all converge onto something whereby we can translate data very easily. I think that's where we are heading.
Okay, and then question number two, which I think you probably half answered already, is have any of your end users, for example, an MCP staff, been involved in the design and or testing of the web app, or are you just about to start doing that?
Well, the answer is not yet for the web app, because it's literally just beginning to stand up on its own feet. But we have worked with the control programs, and some of the people in this room were with us. We had the training sessions for using the GRC-Malaria library. So we've already sort of been working with the partners in country to adopt the tools. Yeah. Yes.
Very wonderful, Dr. So actually, I'm thinking, I wish that I can have this similar to for malaria management system, so we can see all the picture of malaria, not only for GenRe-Mekong. Excellent. And also the data from 2019 up to now, not yet updated, right? Yeah, so what a pity. I just have a minor question. Why in 2016 in Laos, the percentage of drug resistance become 0, and the year before and the year after high, and only that year is 0. So what happened?
I think that's because GenRe-Mekong project has begun in Laos, and there were very few samples collected, and I think that might have caused like some kind of sampling error, where the few samples that we collected also did not have the chloroquine resistance mutation.
Yeah, so I think the answer is that what you're seeing here is a mixture of what we've collected with GenRe-Mekong and what has been submitted by other studies, and there are gaps in between. So it's not like the frequency went down to 0, but the number of samples went down to 0. Okay, yeah. Thank you. Yes, Dr. Siv?
Yeah, very good, ma'am, and indeed, very, very useful when you are finished and national program can use it. And very, very important information. One more thing, I would suggest that whether you need to thinking that how can we link the national treatment guideline in particular period. Otherwise we cannot easy to analyze it when we open it, and there is some resistance here, and we see a letter mutation here. But what is the period at time the national treatment guideline apply drug? pefloquine or chloroquine, so we can have a picture of what is happening.
Yeah,
Thank
that's a very useful suggestion, actually. Thank you.
Yeah, thank you so much for this sound. Really important for policymaker, like we update national treatment guideline according to really sound from Moru or from Welcome Trust or from another partner conduct this activity with Lao PDR. Yeah, and then like we know the for chloroquine, mefloquine resistant. This is the monotherapy, but our national treatment guideline, the first line we use ACT, we try to avoid like mefloquine, right? For example, the as our second line of treatment, we use artesunate plus mefloquine, but we think about the mefloquine resistant. But for the chloroquine resistant for the falciparum so long year ago, but we think about the Ryback, the CQ is sensitivity for PQ, and then this is only for the pregnancy first trimester PV, but our Ryback treatment first line we use ACT. It's really important for us. Yeah.
Yeah, thank you. Congratulations. I think these maps are super, for everyone working on malaria. I have a question about the relationship between the genotype and the phenotype. So first of all, do you think including information on the clinical efficacy to these maps could be an added value? And the second one, sorry, yeah, I'll tell you that. So is the relationship between molecular markers of resistance of SP and resistance chemoprevention, especially for prevention? I think it's not super clear what is the relationship, and I don't think if that can lead to a wrong message to the NMCPs, because chemoprevention with SP is recommended even when quintuple mutants are very high. So yeah, I don't know what you think about that.
I think you're right, and I mean, essentially all the rules that we're using to predict resistance are based on published literature, and as you say, in some cases the jury's still out. And we think that the best we can do at this point is to make very clear what rules we're using, which we're doing, and essentially sort of keep on working to understand how to improve them. So right now, in some cases, they're a bit of a blunt tool, even in predicting, let's say, resistance to pyrimethamine, which DHFR mutation is exactly the key one, and so on. I think all these can be refined over time, but at the moment we're just making it very clear how we're doing it. We're publishing this, and we think that that is the best we can do at present. Fine.
Thank you so much for your nice presentation, and with the very informative presentation, very useful for us in the near future, but not now, because I think in your map until now you update only the genetic marker and genetic data only, and if the Dr. Sip and Dr. Kel would like to link with the update the national treatment guideline for malaria of each country. As you know already, according to the WHO guideline, when you want to change national policy for the treatment of the malaria, you rely on the data of the TES, but not the molecular marker. Only TES data and the molecular marker data in vitro, ex vivo, all of the data is the support for the TS into the replay and update for national guideline. And therefore, I think that in the near future, at the book, you need to add more some data TS and even though EDS inside in parallel with the molecular marker for better. I think the data very important for us to replay and to the update the national guideline. And on the other hand, one the question from the Dr. Thắng asking about the in Laos, the reason why in the year 2016 no data. Maybe you know already in Laos, in Champasak, occurred the outbreak in Champasak with here the first year for the epidemiological ready, and K13 also detected at the end of the 2017, and before the 2017, it seemed to be the no data and no sample, not enough for write out the map. Yeah. Thank you.
I just want to echo everybody that the decision for changing national treatment guideline not only based on TES. These data are also very important because before you change, let's say the reason has been confirmed, whatever TA has been said, you will change to SAM or ACT. You have a choice which drug you are going to change it. If you see the epidemiology data of this, you may know that which drug is the best choice. Because even data is not translated to TS, but there is some resistance or change has been happened through the data. So you have in mind that what drug it should be the best to change. Because they changing national treatment guideline based on your own country. But a recommendation from WHO only the resistance is more than 10%, you need to change that drug. But which drug you choose, you need to see some more information from other. So like the first presentation has been shown, you see a chart, they complement each other. You can see complete our information, you have to see complement each other. One cannot replace the other. Thank you.
So if I can, oh, sorry, Dr. Keo, please, your comments.
Yeah, thank you, Dr. Chief. I agree with Dr. Chief because TES from WHO are okay to like a reference for us for update national treatment guide. But we look at the AP for the genetic also, right? Because the we look at for the epidemiology, another drug resistant. We will think about in the future we should update for the TES. Okay. Definition say, okay, D3 positive, how many percent, and K13 positive, how many percent. But finally, for national treatment guideline, we look at around, not only one WHO. Yes.
Well, thank you. Well, this conversation is music to my ears, and I'm almost touched that we get such good support from the control programs. So that's wonderful. What I would like to point out, though, I mean, of course, policy is a matter for the countries to decide, and each country has rules about this, and the best we can do is to inform. But I think it's very important to highlight a big difference between TESs and genetic surveillance. Genetic surveillance, for all the issues it has, there are certain drugs that we don't have markers for resistance and so on, has the advantage that you can drill into the single drug. TSs, because basically you're not giving one single drug to people. Essentially, in TSs, if you're detecting failures, you've lost both drugs. And in many ways, if we had markers for every drug, genetic surveillance would have more predictive ability, or would be useful in a different fashion. So I think there are complementary approaches in so many ways. And I think it would be reasonable to essentially sort of put pressure on the decision makers to take equal notice of them. I think.